Pseudodifferential operators are better than derivatives. This is a derivative. It measures how functions change. By taking linear combinations of derivatives with smooth coefficients, we obtain linear partial differential operators. Linear partial differential operators can be applied on functions, so a function u and equal a function f to get a linear PDE. Linear PDEs describe many things in nature, like the propagation of waves or the flow of heat. We can actually rewrite this differential equation, or at least the differential operator applied on u, by taking the Fourier transform and then taking the inverse Fourier transform. Now, because the Fourier transform is just an integral, we end up with this expression. Also, the Fourier transform maps derivatives to polynomials, and so in the integrand we have a polynomial p of xi associated to the linear differential operator p. We can use this expression to generalize linear partial differential operators. In fact, instead of taking p only equal to polynomials, we can consider any smooth p that satisfies this bound. We then end up with pseudodifferential operators, which are operators given by this integral, where p is a smooth function that satisfies this bound. Pseudodifferential operators are useful to research mathematicians for a variety of reasons. At number 3 in the list of top 3 reasons to use pseudodifferential operators, we have that every pseudodifferential operator is pseudolocal. This means that they do not create new singularities. In other words, a singular support of Pu, which is the region of places where Pu misbehaves, is small in a sense. It's contained in the singular support of U. At number 2 on the list, we have the representation of regularizing operators. A regularizing operator is an operator that takes a distribution that might be full of singularities and maps it, in fact, smoothly and, in fact, continuously and linearly to the space of smooth functions, smooths out the distribution. Every operator of this type can be represented by a pseudo differential operator with symbol in a class called S of minus infinity, and vice versa. At number 1 on the list, we have the inversion of elliptic operators. So given any elliptic linear PDE, Lu equals f, we can just compose with a pseudodifferential operator p on both sides and essentially invert the equation, solving it at least up to differences in regularizing operators. And it's for this and many other reasons that